Okay, so we will continue on in Chapter 3. I will kind of gloss over, well, we won't be able to spend a whole lot of time in Section 3.3, but you are responsible for learning the content in the book in Chapter 3 or Section 3.3. And I guess I'll just mention two things here, okay? One is mutually exclusive events, also called disjoint events. And what this means is that if A and B are mutually exclusive, then the probability of A given B is 0. The probability of B given A is 0. And the probability of A and B is also 0. Okay? Basically what this means is if A has happened, then B is impossible. If B has happened, then A is impossible. So for example, A could be the coin lands heads, B could be the coin lands tails. Or A could be the dice rolls on a number 1, and B is the dice rolls on a number 2. If one has happened, then the other is impossible, right? If any of you are having trouble seeing the screen, feel free to move closer. Also, don't feel like you have to lean forward and squint. So I see some of you guys doing that. So feel free to move forward. Unfortunately, my handwriting is the way it is. And I hope it's legible enough. Okay, so one nice thing is that the probability of, given that A and B are mutually exclusive, the probability of A or B is then going to be the probability of A plus the probability of B. Okay, this works only when mutually exclusive. We also, there is the general addition rule. Okay, and this applies to OR situations. And that is the probability of A or B. Or here, let me just use different, well, I'll use A or B. But now, in this case, A and B are no longer mutually exclusive, okay? This would be the formula. And this always works for all events. In fact, this even works for mutually exclusive events A and B. It's just that when A and B are mutually exclusive, probability of A and B right here is 0, and therefore it reduces to the mutually exclusive version of the formula. Okay. So you'll have some exercises in the homework kind of going over examples of this. So I hope that's okay. And then just one more thing from section 3.3 that I'm kind of just blitzing through. Can I flip to the next slide? Okay, so still 3.3, and then we're going to talk about multiplication. This is for AND situations. So if we have events A and B, then the probability of A and B is going to equal the probability of A times the probability of B given A. And we kind of saw this already when we did the probability trees. The first branch that you went down could be considered probability of A, and then the second branch would then be the probability of B given A. Okay? And the labels for A and B are arbitrary. So if we called one A and the other B, we could equally validly call them the first one B and the second one A. It doesn't matter. So I'm just going to flip the letters around. And this is also valid. Okay. We have a special case for what we consider independent events. Okay. And what independent events are mean that the outcome of one event has no influence on the outcome of the other event. So if A and B are independent, then the probability of A given B is just equal to the probability of A, because whether B has happened has no influence on whether A will happen or not. So the probability of A, even if you tell me whether B has happened or not, it doesn't influence it. It's just going to be the probability of A. So if I say, well, I'm going to flip a coin, what's the probability it's going to land heads? We would say 0.5. And I say, well, hang on. I flipped this other coin over here and it landed tails. Are you going to change your answer? And you'd say, no, I'm not going to change my answer. Okay? Because we know what happens over here, or even what happened to previous coin flips, has no influence on the next outcome. So likewise, I could flip the labels for probability for letters A and B around. So if I say probability of B given A, this would then be what? Probability of B, exactly. Okay. Here's a question. If A and B are independent, could they also be mutually exclusive? Yes, no, maybe? And the answer is no, okay? The answer is no. Why? Because if we know if they are independent, then what's the case? Probability of A given B is equal to the probability of A. If they are mutually exclusive, the probability of A given B is what? 0, right? Because if B has happened, A is now impossible. Independent means if B has happened, A doesn't care, okay? So we've got definitely distinct situations there, okay? So anyway, this is a kind of an aside. If we apply the multiplication rule to independent events, okay, so if A and B are independent, then the probability of A and B would then be equal to what? Probability of A times the probability of B. Can we see that? So I'm just taking this multiplication rule up here, probability of A and B, which is always true. So this always true. This always works. And I'm just applying our special case of independence, where the probability of B given A is now replaced by just the probability of B. And so probability of A and B simplifies to this. Is that good? Okay, so again, you'll have examples in the homework kind of going over this in the text. There's also a section on density curves, probability densities, and effectively the rule to know there is that we can represent probabilities using a curve. And if you ever took calculus, you can take the area under the curve, and with a probability density, the area is always 1 to indicate all possible outcomes. If you haven't taken calculus, don't worry. You just need to know the total area under the curve is always 1, okay, if we're talking about a probability curve. And that will be, again, mentioned in the book, so we can cover that. So I have to cover the last 2 sections, which are on, bless you, I think, random variables, and a special case of a random variable, which is the binomial random variable. Okay? So random variables can be thought of as outcomes to random experiments or random trials, but the outcome is recorded as a number. If we record the outcome as a number, it's a random variable. Okay? So this is the outcome. These are outcomes to random experiments. Okay? And we record the outcome as a number. And if that's the case, then we have a random variable. So flipping a coin is a random trial, and if we record the outcomes as heads or tails, then that's not going to be a random variable. However, if we say heads is 1 and tails is 0, then it is a random variable. Okay? So with a coin flip example, okay, so outcomes, heads and tails, can be quote-unquote coded to 1 and 0. Okay? Then we have a random variable. Okay? And we might call this random variable capital Y. This represents the outcome of the coin flip. And we would write statements like the probability that y ends up 1 is equal to what? 0.5, right? And we would say the probability that y ends up as 0 is 0.5, okay? And again, this is kind of a slightly simplified version of the world, but then this would account for all possibilities. When we flip a coin, we're either going to get heads or tails, but those are coded as 1 and 0, and therefore we have a random variable, and we can make statements like this. Okay? We can have more complicated situations. Okay, and so for example, this is apparently there's some freshwater fish. I have no idea what it is. I'll look this up actually. Freshwater fish. Here, let's. It's Cottus rothius. I think this is an ugly looking thing, but oh look, somebody's looking at the same homework solutions. Hey, look, oh, all of the images for, okay, here we go. Is this it? No, these don't look the same. Okay. Okay, this apparently is what the fish look like. All right, maybe. Okay, so apparently these fish have a certain distribution, and when you pick a random fish in the water, so this is why it's a random trial, right? So the random part is that I'm selecting a random fish from the water. And again, I'm not sure how we're getting random fish, but let's say we could get a random fish. And what we're going to do is we're going to count how many vertebrae are in its back. So we're going to have to kill and cut open the fish, and we're going to count how many vertebrae there are. So that number of vertebrae is a random variable because there's a random process of selecting a random fish, and then we're recording our results, which is a number, the number of vertebrae. Okay? Does that make sense? It's just like I could select a random person and we could measure this person's height or weight. That would also be a random variable. Okay? So we're looking at freshwater fish. We're going to select a random fish. Okay? We count the number of vertebrae in the fish. Okay, so the resulting number is a random variable, and I'm going to just abbreviate that RV. And we have a little table telling us how common certain numbers are. Okay, so we look at the number of vertebrae. And we're going to say the percentage of fish. And somehow, again, this is a textbook example, so we're pretending we know these numbers, okay? And apparently there's only 4 types of fish. Fish with 20 vertebrae, fish with 21, fish with 22, and fish with 23. And there's no other fish in the world, at least for this species. 3% of the fish have 20 vertebrae, 51% of the fish have 21, 40% of the fish have 22, and 6% of the fish have 23. And there's no other possibilities for number of vertebrae. When you pick a fish, it's going to be it's going to have one of these 4 numbers, and this is how common they are. Okay, so we could ask a question like, what is the mean number of vertebrae that we will encounter? Okay, and so to get the mean number of vertebrae, we would not take these outcomes, add them up, and divide by 4. Do not do that. We have to weight each of these outcomes by how likely those outcomes are. Okay, so we have to get a weighted average. So, but that is going to be called the mean, which is represented by this letter mu, is also known as the expected value of y. Okay, so this is mean mu, also called the expected value of y. And the formula for that is we're going to take each value y, each possible outcome, and we multiply it by the probability of getting that outcome. And we're going to do this for all possible outcomes, and we add it up for all possible outcomes. Is this formula okay? Okay, so I'm gonna here I'll label these. So we take each value, each possible outcome. I hope you can read this. This says each possible outcome multiplied times the probability of that outcome. Okay, so maybe I'll do 1, 2, and then lastly, we do this for all outcomes and add them up. For all possible outcomes, and add them up. We're good now, I hope? Okay, so let's try this out. I'm gonna just copy this lower half here. You don't have to, but I've run out of space on my screen. Okay, so let's try this. So we want to know what is the mean number of vertebrae that I will select. So I'm going to say, okay, well, 20 times, what's the probability that I select a fish with 20 vertebrae? 0.03. Okay, and then 21, and what's the probability I select a fish with 21 vertebrae? 0.51. And I do this for all possible outcomes. And if you have a scientific calculator, usually you can just punch this in one go because it understands order of operations. And I punch them in and I get 21.49. Okay, so my mean, mu, or my expected value of y, is 21.49. This is coincidentally very close to what I would have gotten if I added these up and divided by 4, but it is distinct from that. And so depending on the situation or the circumstance, you might get a number that's close, but it is not the same. You cannot just add them up and divide by 4. Yeah.
Since this is a sample and not a population where
this is a population. This table represents the distribution in the population.
Oh, okay.
Okay, so again, this is just a textbook example that we're making up, but this is the table of the distribution of fish in the population. So when we're learning rules of probability, we're just kind of announcing this is what the population looks like. Okay. When we deal with statistics, we take into effect that it is a sample. But when we're learning probability, we just say, hey, this is the population. What can we learn about it? What can we say regarding probability? Okay. All right, and so this notion of expected value or the mean is that if I were to repeatedly catch fish and count how many vertebrae, and again, this concept of in the long run, if I do this an infinite number of times, continually write down, oh, here I got a fish with 22, here's a fish with 21, here's a fish with 22 again, here's a fish with 20. And I continually do this, and I keep track of every single one. After, you know, 1 million fish, and I take the average, I would get this number here. Okay, so this is the, quote, long run average after many observations. I should say many random observations. So actually saying I caught a fish is technically not a random observation, but we're pretending that it is. Okay, and so that is how we get the mean mu of a random variable. Okay, so with that notion, what is the mean number of heads that I would see in a coin flip? So remember, we said heads will be equal to 1, tails is equal to 1. Probability of heads will be 0.5, and probability of tails is 0.5. We've coded the heads to be 1, and we've coded the tails to be 0. So what is mean number of heads in a coin flip? It would be 0.5. I would take each outcome, right? So one possible outcome is 1, and how often do we get the number 1? We get it with probability 0.5. And then the other outcome is 0, and how often do I get 0? With probability 0.5. And so when I do this, I get 0.5. This is my mean, or expected value. Yes?
So you know how you gave tails the number 0?
Yes.
What if you gave it the number 2? Or do you always have to start with 0?
You don't always have to start with 0, okay? But then if you gave tails the number 2, you would have a different interpretation to the question, okay? Because instead of asking, so instead of saying what was the outcome of the coin flip, heads or tails, what I did was I changed the question so it would be a random variable. I said, how many heads did I see? And either I saw 1 head or I saw 0 heads. And that's why the assignment was 1 and 0. If I wanted to say 1 or 2, you would have to ask a different, the interpretation would be different. Maybe you have a coin, but then maybe on one side you write the number 1, and on the other side you write the number 2. And what you're doing is you're keeping track of what number shows up, and then the question is, what is the average value that shows up? And then it would be correct to use 1 and 2 in that case. But it is no longer correct to use 1 and 2 to answer the question, what is the mean number of heads that I see? Unless you get some foreign coin where you have 1 head on one side and 2 heads on the other side or something, you know. So, you know, when we ask these questions, there's some kind of translation from into a number here. Yes.
Question. So I understand the coding, but then they're each one on the other side. I kind of missed what that was.
Oh. Yeah, what? Now I'm confused myself here. Okay, let's just get rid of this over here. Sorry. I apologize for that. Okay, is this okay? Creation of calculating the mean or expected value of a random variable. Okay. So once we have the expected value, we can then also ask for the variance and standard deviation of a random variable. What is the relationship between the standard deviation and the variance?
Standard deviation is the square root.
Standard deviation is the square root of the variance. Why do we even bother calculating a standard deviation or variance? What does it tell us when we're talking about a sample of data? Spread, okay? And so you could imagine, so in this population of fish, okay, we're much more likely to get what numbers than what numbers? Yeah, we're much more likely to get 21 and 22 than we are to get 20 or 23, okay? And so would you expect your variance, your spread, to be high or low?
Low.
We would expect it to be low, okay? Now, maybe there's some other population of fish where all four values are equally likely. And in that case, would we have more variance or less variance? More variance, okay? And so in the same way we can talk about the spread in a data set, we can talk about the spread in kind of this, in a population for a random variable. Okay, we can talk about the spread in a random variable saying, I'm expecting there to be wild variation between the values that I get. Okay, here's another, maybe variance and standard deviation of a random variable. Okay, let's say there is a game. Okay, let's say you go to Vegas and we have two games. Okay, two games available. In one game, let's say both of these games cost $1 to play, and in one game, you can the outcome is you win $0, so basically you lose, okay, or you win $1,000, okay. So I don't know, maybe it's some game you pay the guy you pay the guy $1, and then I don't know, you spin the wheel or something, okay. Now I don't think anything in Vegas has these odds, but let's just say okay, so the probability of winning 1,000 will happen with probability 0.00095, which means the probability of the opposite happening would be, what is that, 0.00095, probability 0.99905. Okay, and then the other game, game 2, let's say this happens with probability 0.475, which means this happens with probability 0.525. Okay. Okay, so for both games, what is the what is the expected value for game 1? What's your expected winnings in game 1? Yeah.
What about the probability if you don't do anything, like don't even play the game?
We're not going to consider that. We're going to just say when you play the game, these are the probabilities of what's going to happen. Okay? So if you play game 1, these are the probabilities of what's going to happen. 95 cents, right? I do 0 times 0.99905 plus 1,000 times 0.00095, and I get 95 cents. Meaning, when you pay $1 to play, your expected winnings is 95 cents. Okay? And so this game could probably exist because the casino maintains a small edge. Okay, what about game 2? What is the expected value for game 2? It's the same, right? I've tried to pick these numbers so that we have this. I would do 0 times 0.525 plus 2 times 0.475, and I get 0.95. Okay. Now, obviously, if you were to just add up 0 and 1,000, divide by 2, and 0 and 2 and divide by 2, you would get the wrong answer, right? Okay, so think of these games, and which game has more variance in the outcome? Game 1, right? Which game would be more exciting to play? Probably game 1, right? I don't know. Maybe, I mean, it's... I guess it's exciting to double your money when you win $2, but you could also imagine the worst game in Vegas. So this is not a game, but you know, I could have quote game 3, where they're just like, oh, thanks for coming to Vegas. Let's just cut to the chase. You win 0 or you win 1. You play $1, and this happens with 5% probability, and this happens with 95% probability. So essentially, you're giving them $1 and or actually, no, this is actually not even the worst game. The worst game would be win 95 cents with probability 1. You give them $1 and they give you 95 cents in return, and they say thanks for playing. This is always going to happen. Over here, there's the expected value would be 0.95 times probability 1. You get 0.95. What's the variance of this game? 0. There's no variance because there's no more chance. It's just every time you give them $1, they're giving you 95 cents back. There's no variance in what the outcome here. Okay, so this has variance of 0, the variance here is equal to 0, and the standard deviation would also be equal to 0 because there's no variation in the outcome. Okay. Over here, the variation would be fairly small in that you're either going to win $2 or 0, okay? You're not going to play this game to try to get rich quick, okay? This is not the plan to get rich quick. Well, neither of these games are the plan to get rich quick, but if you wanted to try to get rich quick, the one that you should try would be this one. It's very unlikely that you'll win, but you might win, and when you win big. You win $1,000, okay? And that's kind of what those flashing lights and all of those slot machines try to lure you in by. They have this giant number that says you might win, you know, $100,000 or whatever, and they're increasing the variance of winnings, which makes the game a little bit more exciting, But of course, the associated probability with winning $100,000 is incredibly small. Okay, so this will have, game 1 will have high variance, and game 2 will have lower variance. Okay, so let's talk about how to calculate these quantities of variance. Does that make sense? This concept of variance of a random variable? I hope. Okay, so to get our variance, the variance of some random variable y, what we do is we take, for each outcome y, we're going to subtract off the expected value mu. We're going to square that difference and then multiply that by the probability of getting that particular outcome. Okay, so let's do game 1. The outcome, y, is either 0 or 1,000. The associated probabilities are and we know that mu, because of the previous calculations, we know that mu is equal to 0.95. Okay, so to get our variance, we take the outcome 0 and we subtract off our mean of 0.95. I'm going to square this difference, and then I'm going to multiply it by the probability of getting this outcome. And then I do the same thing with the other outcome. So I would write what? 1,000 minus the mean of 0.95. We're going to square that difference, and I'm going to multiply it by the probability of getting that outcome. So I got, I'm going to do parentheses, parentheses 0 minus 0.95, close parentheses, squared, times 0.99905, plus, parentheses 1,000 minus 0.95, close parentheses, squared, times 0.00095. And I hit enter, and I get a variance of 949.0975. And so my standard deviation is then the square root of this. I get a standard deviation of 30.81. And the nice thing about the standard deviation is that the units are in the same unit as your random variable. So in this case, it would be a standard deviation of $30, $30.81. Is that okay? All right, and so just very quickly, I'm going to just do this for game 2. Forgot what the 0.475. Again, we have a mean of 95 cents. So you have to calculate the mean first by doing the weighted average. And so in this case, the variance of y for game 2 would be 0 minus 0.95 squared times 0.525 plus 2 minus 0.95 squared. here I get a variance of 0.9975 and a standard deviation of, square root of that, 0.9987. Okay, so essentially a buck. We have a standard deviation of $1. Over here we have a standard deviation of about 31 bucks. How are we feeling? Random variables? Okay, so we can calculate. So when we're talking about, so again, just so we don't lose sight of the big picture here, we are talking about the outcome to some random thing. So in our case, we used outcomes to games of chance in Vegas, or some other place where you're playing games of chance. The outcome is a number. It's how much money you win. Each of those outcomes have an associated probability, and so we want to know what is the mean outcome that you can expect if you were to play this game thousands of times or millions of times. Well, in the long run, you're expected to win about 95 cents every time you play. We can also look at the variance and seeing how much variance is there from play to play, and we see in certain circumstances, even if the average is the same, you might have a lot more variance in the outcome. Okay, and so this is just a simplified example, and you've got some examples in your book. Is that okay? All right, so with our last bit of class, I have to cover a specific type of random variable, and this is known as the binomial random variable. Okay. And I'm just going to deal with the version with counts. Okay. The book also talks about proportions. But I prefer to deal with just counts, okay? And that's just because if we say I'm going to take select 100 people, what's the probability that if we were dealing with proportions, I could say what's the probability that 50% are male? That's essentially the same thing as asking what's the probability that 50 out of 100 are male, okay? And I think the calculations are just much more straightforward when they're counts than when they're proportions. So when the book talks about proportions, immediately what I do is I just convert the proportion into a count and then solve the problem that way, rather than trying to answer the question directly as a proportion, okay? So the book mentions proportions. My method is to convert the proportion to a count and then solve. So to convert, just do P, the proportion, times N, the count, to get your, N would be the sample size. Okay, so that's just an aside regarding this. Okay, so let's go back to what binomial random variable is in the first place. Okay, and these are outcomes to specific random situations where we are repeating essentially a coin flip. Not necessarily a coin flip, but we're repeating a trial that has only two possible outcomes. Either something happens or it doesn't. Okay? So we repeat a random trial that only has two outcomes. So that's why it's called binomial. We repeat the trial n times, And we are interested in getting, and this is where different textbooks differ. The letter that our textbook uses is J, okay? We're interested in getting J, quote-unquote, successes, all right? Success is an arbitrary label that we apply to basically a yes or no variable. So we're asking, did this happen or did this not happen? We arbitrarily label one of them to be success, okay? It could be, I'm randomly picking 100 people. What is the probability that 20 of them have some disease, okay? In this case, we would label the disease, having the disease, as a quote success, even though it's not a success in any traditional meaning of the word. So examples of binomial, and I hope this kind of clears what we're dealing with here. So we randomly select 50 people, okay, and we want to know the probability that someone has, we'll say, type O blood is, we'll say, 44%. And we're asking, what is the probability that 22 out of the 50 have type O blood? Okay. Oh, and I'm sorry, I forgot one thing here. We repeat the trial n times. We're interested in getting J successes, and I'll say the probability of success is P for all trials. I apologize for inserting that in later. Okay, so in this case, we are repeating a random trial, which is a random selection of a person, right? I'm randomly selecting a person. I'm doing this 50 times. Every time I select someone, there's a 44% chance that this person has type O blood, and I'm interested in the probability of getting exactly 22 out of 50 people having type O blood. And does this question make sense? Okay, another scenario is I flip a coin 10 times. Okay, what is the probability? Okay, and we'll say it's a fair coin. So probability of heads is equal to 0.5. What is the probability that the coin lands heads 8 times out of 10? Okay, 8 times with out of 10 implied because I've flipped the coin 10 times. Okay. So these are both examples of binomial random variables. We're repeating some random process n times. Every time I repeat it, the probability of getting a quote success, whether that's having type O blood or landing heads or whatever it might be, has the same probability. 0.44 every single time or 0.5 every single time. And what I'm interested in is getting a particular number of successes. So these are binomial outcomes. Another one is maybe Kobe Bryant takes 10 free throws, okay? Every time he throws the ball, he has a 90% chance of making the free throw. What's the probability he makes all 10 free throws? Or something like that. Or what's the probability he makes 8 out of 10? Or what's the probability he makes 9 out of 10? All of these are binomial situations. You're repeating the same thing and there's, like, with the Kobe Bryant example, we're assuming that every time he takes a free throw, he's got the same probability of making the free throw, which may or may not necessarily be the case, but we can just say this is a simplified version of the world, and we're going to assume that this is the case. Okay? So to answer this, okay, so let's do maybe an easier version. Okay, so I will flip a coin 4 times. Okay, fair coin. So probability of heads is 0.5. And I want to know, what is the probability I get 3 heads after 4 coin flips? Okay? Or I could have flipped this around and I could say a family will have 4 children. They decide to have 4 children. What's the probability that they get 3 girls? Okay? Assuming that the probability that each child is a girl, it has a probability of 0.5. Okay? So that's basically the same type of question, right? So this is essentially what we're asking. So how would we answer this? Okay? Well, this can be thought of as a sequence of independent events. Okay? And so we could get, one way to get, this is actually not the best example. One way to get 3 heads is to get heads, 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 and then tails. Okay? And so the probability of getting heads, 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 and then tails would be 0.5 times 0.5 times 0.5. This is heads times probability of heads times the probability of heads times the probability of heads. And then times the probability of tails. What is the probability of tails? It's also 0.5, but it's technically 1 minus 0.5. Is that okay? Because probability of heads, we're saying, is 0.5. So the probability of tails, or not heads, is 1 minus 0.5. I should have actually used a different example here. And so this probability ends up being, if you'll forgive me for leaving it this way, is it's going to be 0.5 raised to the 3rd times 1 minus 0.5 raised to the 1. And yes, I realize this is actually just 0.5 raised to the 4th, but please indulge me in leaving it in this form. Is this okay so far with everybody? Okay, but this is not the only sequence that gives you 3 heads. Right? There are other sequences. I could also have heads, heads, tails, heads, heads, tails, heads, heads, and tails, heads, heads, heads. Okay? So there are 4 possible ways to get 3 heads. And each one of these, if I were to calculate this probability, each one would also be 0.5 raised to the 3 times 1 minus 0.5 raised to the 1. Is that fair to say? Because they all have 3 heads and they all have 1 tail. Okay? And so the total probability of getting 3 heads would be actually 4 possible ways times the sequence of 0.5 raised to the 3 times 1 minus 0.5 raised to the 1. So this is, number 4 is number of possible sequences. This is, the second number is probability of success raised to the j power, because we want j successes, right? And over here, this is probability of non-success or failure raised to the n minus j power. Because if we're going to have a total number of n trials, j of them have to be successes, which means the remaining part, n minus j, has to be non-successes. Are we doing okay? Yes, question.
Yeah, but I just want to know, is there a shortcut to finding the number of possible sequences?
Yes, I will talk about that on the next slide here, okay? So I'm hoping this part's okay, and forgive me that I used this example with 0.5. It would be more clear if I had used a unfair coin or something, okay? But so getting the total number of possible sequences. This is now entering the land of permutations and combinatorics. All you have to know is that we have this thing called the choose formula. Okay, and we will say something like n choose j. And this is also written like this. N choose j can also be written as n choose j. And this basically means is with a sequence of n total and j successes, how many arrangements are possible? Or another way is, if you have n items and you're going to choose j of them, effectively you're choosing j of them to be successes, how many ways can you choose j items? How many combinations are possible? Okay, so the formula for n choose j is n factorial over j factorial times n minus j factorial. Okay, don't worry about this. You've got a button on your calculator right here. Okay, if you got mine that says NCR, perhaps in your, if you have a Texas Instruments calculator, maybe you have a math button or a probability button. Okay, maybe you have to hit math and then navigate to PRB, or maybe you can hit PRB directly and then you'll find NCR, okay, somewhere in there. Okay, so we could have answered this by saying for choose 1, and it says, oh, there's 4 ways to do this. Okay, we could say if I'm going to flip a coin 10 times and I want 5 heads, what would I do? I would do 10 choose 5, right? So 10 flips, we want 5 heads. How many arrangements? We would do 10 choose 5. Can also be written 10 choose 5. So on the calculator I would do 10 shift divide 5, 10 choose 5, and it says there are 252 arrangements. Is this okay? Can I go to the next slide? Okay, and so putting this all together, okay, for binomial, okay, we have n trials, j successes, and P is probability of success. Okay, I should say want J successes. So then the ran out of battery here. The probability that y is going to take on the value j is going to be equal to choose n, choose j. This is the number of sequences that are allowed, times the probability of p raised to the j, times the probability 1 minus p, which is the probability of failure, and it's going to have to raise to the n minus j. Okay, so you can use this formula to answer questions like, if Kobe Bryant takes 10 free throws, what's the probability he makes 8 of them, assuming he has a 90% chance every time he takes a free throw, or something like that. Okay. We can also ask, what is the mean of the random variable y? So this would be mu, and there is a nice answer, and that is just n times p, and this, I think, makes sense. If you flip a coin 10 times and the probability of getting heads is 0.5, what would you expect in the long run? You would expect 10 times 0.5, or 5 heads, okay, overall. Of course, anytime you flip a coin 10 times, you're not necessarily going to get 5. You might get 6, you might get 4, or some other number. But in the long run, we would expect 5, and so that would be the mean. And then the variance is going to be n times p times 1 minus p, and the standard deviation would then be the square root of n times p times 1 minus p. Okay, so we will end there. Be sure you do your homework. We will have a quiz next week. It starts right at the beginning of class, so make sure you arrive here on time, 7 o'clock. Okay, good luck.